Hello. In today's video, we are going to learn about a geometric distribution, which is a very good example for a discrete random variable. A geometric distribution is one among a discrete random variable. A geometric random variable is the number of independent trials until the first success when the probability of success on each trial is a constant. So let us see. The geometric distribution is usually denoted by the parameter p, where x is the number of trials until the first success, and p is the probability that the given trial is a success. Q is the probability that the given trial is a failure. P is your success, Q is your failure, and the x is the number of trials until you get the first one to be a success. So in fact, a geometric random variable is the number of independent trials until the first success when the probability of success on each trial is a constant. So it is unlike a binomial distribution. This is a little larger. When you compare to a binomial distribution, geometric random variable is arbitrarily large, where the binomial is NP and the geometric is just P. The geometric random variable has to be at least 1 because at least one trial is needed to get the first success. Whereas in a binomial, you can have between 0 to n, but in a geometric distribution, you must have at least 1. And in a binomial distribution, the probability mass function, that is p of x equivalent to x, is q raised to x minus 1 times p. Since they are all independent events, you are getting a success after x number of times. So the previous xth attempt you are getting a success. So the previous x minus 1 attempt will be a failure. The first is a failure, second is a failure, third is a failure. Like that, x minus 1 failures you have, and xth item is your success. So it should be q times q times q x minus 1 times multiplied by p. So it is q raised to x minus 1 times p. And the cumulative density function is you are accumulating all the probability mass function, which is p of x less than or equal to x, which is nothing but the summation. And in this discrete distribution, you can find the expected value, the two variables, expected value and the variance. And the expected value, using the formula of sigma x p of x, you can prove that it is 1 over p. And the variance of x is q by p squared. These two can be easily solved, and the formula to find the expectation is 1 by p. Variance of x is q by p squared. So let us see an example here. Assume that the probability of a defective computer component is 0.02. That is, the probability of success is 0.02. The components are randomly selected. So let x be a random variable. Your x is the number of computer components tested until you find the first one to be defective. Find the probability that the first defect is caused by the 7th component tested. That is, you're asked to find p of x equal to 7. And also, how many components do you expect to test until one is found to be defective? That is, you are asked to find the expectation of x. We need to find what is p of x equal to 7, and we have to find the expectation of x. If we are finding P of x equal to 7, let us make use of the formula, which is q raised to 7 minus 1 multiplied by p. So which is q raised to 6 times p. What is your q? Q is 0.98 because p is 0.02. So it is 0.98 whole raised to 6 multiplied by 0.02, which gives you 0.0177. If you want to use your TI calculator, make use of the second variable which gives you the distribution and scroll around, go down and search for the geometric PDF. The syntax is geometric PDF PK. In our case, P is 0.02. The kth item is the seventh item. So just enter the syntax geometric PDF 0.027. You get 0.0177. So this matches with the result what we got earlier. So we are also trying to find the expected value. You know that the expected value is nothing but the mean, and the expected value is 1 over p. So 1 over p is 1 over 0.02, which gives you 50. So you have to search for 50 computers and at least 50 items to test. The number of components that you will expect to test until you find the first defective will be 50. Maybe the 51st item may be a defective item in order to get the probability as 0.02. You can also find the standard deviation and variance. The variance formula, the standard deviation is nothing but the square root of the variance. So those results can also be obtained in this case. For the same question, if you're trying to graph the function p of x equivalent to x, which is the probability mass function, for this given probability 0.02, the probability of success to be 0.02, you can get this graph using a MATLAB. And in this case, y-axis contains the probability of x. So when x is 1, you get the probability, x is 2, you get the probability, like that. You can go on, find the probabilities where p is 0.02. So we have not only calculated when x is equal to 7, you've got the values when x is equal to 1, 2, 3, etc. goes on. So the exponential curve looks like that. Sorry, the geometric curve looks like this. Here we have another example of the geometric distribution, COVID-19. The official data on the spread of the Wuhan coronavirus continues, and it suggests that the growth rate is geometric. It is a geometric progression. It is a geometric random variable, and you can get a geometric distribution. So maybe in this case, in the second case, the growth rate is positive, whereas in our first example, the growth rate is negative. So try to think about these two examples, compare the two examples and see whether the second example, what I have discussed here, will fall under the geometric distribution or not. Maybe this is for the researchers to find out whether it falls under a geometric distribution or a logarithmic distribution. So today we talked about a geometric distribution, and we saw two different examples to explain the concept of a geometric distribution and to see the graph how it goes. Thank you for listening. Thank you for watching this video, and thank you for being patient. Thank you.